A new CAD/CAM method has been developed at Great Lakes Orthodontics to digitally design and produce occlusal splints. The process results in the flattest and smoothest possible surface, with the accuracy of restorative CAD/CAM systems. Conventional laboratory methods typically result in indexing marks in the functional surface, as shown in these micrographs of a standard lab-produced splint. These divots tend to lock the patient in place and inhibit the free movement needed to relax muscles. Digitally produced splints have smooth functional surfaces, providing a skating rink effect that allows patients to freely contact the splint surface without being locked into place. Digital design ensures consistency. And high-speed machining provides an accurate and smooth splint surface. The process includes scanning, articulation, splint design, and milling. The process starts by laser scanning upper and lower plaster models. Several individual scans are taken, which are merged into a single object. This results in a three-dimensional model of the upper and lower arches. The models are calibrated with respect to the mounting plate. This allows them to be accurately positioned and moved as they would be on a standard articulator. After the models are scanned, the case is articulated. For mounted cases, the models are positioned exactly as they would be on the specific articulator used. Here, the y-axis corresponds to the centric axis for the SAM articulator system. Unmounted cases are articulated using average anatomic values. First, a lower occlusal plane is defined and set at an angle to the horizontal. A hinge axis is then located at a specific axis incisal distance and vertical height. The articulation is readily changed based on patient-specific data. Here we see the effect of changing the lower occlusal plane angle, the axis incisal distance, and the vertical height. Condylar geometry is also under software control, including the condylar inclination angle, eminence curves, and the Bennett angle. Splint design starts with setting the opening. The bite should be in centric relation and ideally close to the desired splint thickness. It is important to be able to look through the occlusion to ensure no lateral interferences. Next, contact points are defined. As the designer clicks on the model, software automatically repositions the points to the highest location on the tooth with respect to the occlusal plane. An island area is defined at the contact point. A smooth plane is passed through the islands to form a contact surface. A portion of this plane becomes the splint surface. Software allows the flattest splint to be designed by omitting contacts that tend to unnecessarily angle the contact surface. For contacts on teeth associated with large curves of SPE, the arc of closure is used to optimize points instead of the occlusal plane. Here we see a complete set of contact points. The perimeter of the splint is defined by clicking a series of points on the model. The splint can now be computed. The splint surface smoothly passes through all of the contact points. For centric relation splints, the extent of the anterior and cuspid ramps is defined by placing markers on the contact line. Here we see a complete set of contacts on a lower model. Software also allows the width of horizontal shelves adjacent to the ramp to be specified. Here we see a CR splint designed without a shelf, a 1 mm shelf, and a 2 mm shelf. Three-dimensional CAM software creates the tool paths and strategies used to cut each splint. Regions of the splint surface that have contact points can be specifically chosen for machining. The splint model is covered with acrylic and mounted in the milling machine. The acrylic is machined down to the splint surface with the accuracy of standard CAD/CAM systems used for crown and bridge. Progressively smaller tools are used to sculpt the surface. Splints can be made from hard acrylic, thermoformed clear polyester, soft lined materials, as well as thermal active acrylics. Wire clasping is also accommodated for using software. With almost 1,000 cases performed during beta testing, the reliability and performance of this technology has been demonstrated. Occlusal splints with flat, accurate, and reproducible surfaces can now be routinely produced.